Hola, buenos días. Bueno, esta es la última ponencia de seguridad.
Hello, everybody. Welcome. This is the last roundtable that is devoted to security. We'll try to make this as entertaining as possible, since we are approaching the end of this seminar. The 21st century has brought us many technological advances and progress. And this, of course, entails great challenges. And these challenges have to do with the needs of population. We see that population has grown, and that has had great impact in our planet. Today we're here to talk about large infrastructures, fracking, and the aerospace industry, and more specifically, satellites. The first person that is going to take the floor is Luis Cosano, who is an engineer. He studied at the Polytechnic University of Madrid, and he specializes in foundations and structures. He studied an MBA and EIO. He has more than 15 years of experience in the maintenance of large infrastructures, and he currently works in Freycinet, which is a French multinational that specializes in the repair and reinforcement of structures. Luis, you have the floor.
Buenos días a todos. No quisiera empezar mi ponencia sin darle las gracias en nombre de Freycinet a Mafre Global Risks.
I'd like to thank Mafre Global Risks for the invite, and I'd like to thank Maite for chairing this table and for coordinating and putting together this roundtable. Thanks for your patience. We're going to talk about the Cádiz, the bridge, and the truss system. For those of you that don't know, Cádiz is in the south of Spain. Since the 60s, the mayors of the city of Cádiz, in view of the traffic congestion, decided to build a bridge in Cádiz. And during the year 2009, a series of projects were presented for the construction of this bridge, and in the end, we decided to go for the Rio San Pedro option. This is a bridge over the Bay of Cádiz that closes access to the industrial park of Navantia. And thanks to this third access, the congestion is much lower. This is 3-kilometer long bridge. There you have the technical details. It has 2 lanes with 3 runways, 2 hard shoulders, and 2 sidewalks. But those 2 sidewalks are not intended for pedestrians, but for the use and the maintenance of the structure of the bridge. There you have a picture of the bridge, almost ready to close, and we've worked on the last span of the bridge this week. These are like 4 bridges in one. It has 4 stretches. There's a first stretch with a total length of 581 meters and main spans that have been subject to variations. We have built this bridge with a tower, thrust tower, and section or stretch number 3 is the one that has been subject to a greater number of modifications, design modifications. At the beginning, we considered an oscillating stretch. In the end, we decided not to go for this option. We listened to the requirements of the companies of the industrial park, among them Navantia, and they asked us for a stretch with no height restrictions. And here in stretch 3, it's 150 meters long stretch that can support 4,000 tons of weight and 50 kilometers of welding in total. There you have the manufacturing of this isostatic bridge and the assembly. We transported the different sections using boats, and then we did heavy lifting and rigging in order to place the different structures and put them together. Now I'm going to talk about the truss, and we have been in charge of the truss. And here you can see all the details. Total length is 1,207.50 meters. It's as for the cross-sectional cut, it is very, very broad, 32.5. It's the first time that a bridge of this kind is built in Spain. And Carlos Fernández Gasado is the name of this bridge, and it's also the name of the engineering company that has designed it. There you see the main span of the bridge under construction. And we had to fix the bridge using the cables. And the last section, section 8 to 10, is pretty long, 1,182 meters. And that last stretch aims to maintain the aesthetics of the rest of the bridge with pillars or pylons. And there you can see some images, and you can see the changes in geometry or in shape, and the landing of the bridge to the surface. These pylons, as you can see, are pretty broad. As for the cables or the stays, we have introduced many of them in order to give it the adequate strength. These stays have anchorings using tendons or cables. 80 tendons or cords in total are used in some of the stretches, and in other stretches the number of cords is reduced to 37, and this number increases again in the final stretch of the bridge. This is an all-time record here in Spain regarding the length of stays, in total more than 290 meters. But we're not the world leader. This is the Rusky Island, which is 1,104 meters long, that has 168 stays, and the longest one is 582 meters long. So they take the lead by far. This bridge is a milestone in Spain because of the height it allows. It allows for vessels of up to 69 meters of height to go under the bridge. It's the second most important of the world in terms of height. Number one is a bridge in New York, and its height is even greater than that of the Golden Gate. Let me go back to the stay system. I brought this picture so that you can see the cladding first, and then you can see the conduits. These tubes or pipings that are introduced into the concrete structure, and then you have the part that is above it that has different housings that are covered with plastic now. and we're waiting for the buffers. And these stays have hydraulic buffers to reduce vibrations that are produced by water and wind. To the right, you can see the white cladding coming out of the metallic tube, and that cladding is fingered. And the idea is to control the water flow in order to reduce the vibration caused by water. As for the technical challenge that Freycinet has faced during this project, these could be described as three: the longitude of the stay, the isotension, and the buffers. Well, it's a very long length. The cladding is very long as well. We're talking about many connections. As for the tensions, these of 91 cords require fastening, and we had to carry out 6,000 fastening operations. Not all the cords are fastened 2 times, but to modify the geometry of the bridge, we had to constantly refasten them. These stays are the first in the world where the fastening force exceeds 50% of the break limit of the cord. So we have had to design a new aluphomatic system. As for the buffers, this is the first time that a Spanish team installs these kind of buffers. And as for the risks that we have encountered, we have the project errors. You need to consider that during the construction stage, these bridges are live structures, so they move, they go up, they go down. There are changes in the structure. There's movement. Sometimes we're talking about spans of 400 or 500 meters. We have also suffered execution errors. The cords must never come into contact with the tube. And another of the problems is the alignment of anchorings and tubes. The stay or the cord is never, straight. There's a curve involved. And then we have the communication mistakes. These projects are long-lasting. We received 560 documents from the client and generated more than 16,000 files for the execution of the project. As for the risk inherent to the system, the galvanizing of the cord, the wedges, conductivity of the anchorings, the cord has a triple protection: the external cladding, which is white, plastic or polyethylene, and a galvanized coat. An excess in galvanization can lead to excessive filling of the wedge. That cord is 15, has a diameter of 15 millimeters, and can resist between 10 and 12 tons. So we use that conic structure or wedge that is then housed or lodged in the structure, and as a result of the strength of the cord, it is introduced in the block, and then the whole structure is blocked. How do we control these risks? Well, through training. It is essential that people know what they do. Procedures. It is essential as well that people are very much aware of the procedures, because the procedures contain the know-how of the company. It's complicated to manage the control of the training and to make sure that the know-how isn't lost. But at the same time, you need to work constantly to ensure that your staff are duly trained and know what they need to do at every moment. And there's the racing as well that is very, very important. These works are not too complex in terms of execution, but they are highly repetitive. The tasks involved are very, very repetitive. And when this happens, there's this loss of control, and human beings tend to get a bit more relaxed, and they become less rigorous, and that leads to mistakes. And during the execution of the works, it's very important to ensure quality assurance, and we need to adhere to the procedure and not focus on filling out documents, and we're used to huge amounts of red tapes, but if we want to assure quality, we need to adhere to the procedures and do things correctly. And it may seem obvious, but we're talking about people that are often working at 300 meters of distance, so communication is essential here. And we need to use communication codes to ensure adequate communication. In the aerospace industry or in aircrafts, the way the workers communicate are based on codes. And perhaps we in the construction world have very much to learn from these sectors where these codes are much more advanced. And to finish up, I'd like to mention that very few things happen, but and these so because things are done properly. When that's not the case, the risks flourish and accidents occur. Here we have a passageway in South America, and 2 months ago it collapsed. The states are manufactured by Freycinet, and as a result of a series of errors and failures, because these mistakes cannot be allocated only to one sole person. There are always multiple causes. Well, the truth is that when the passageway was mounted, it ended up collapsing, and that brings my presentation to an end.
Muchas gracias, Luis, por tu gráfica presentación.
Thanks for your presentation. We're going to move on now to the next panelist, who's going to talk about fracking. Raquel Fernández is a chemical engineer. She studied at the Complutense University of Madrid, and she also studied prevention and safety at the workplace. She has worked in Repsol since the year 2000. She has held different positions, and she has worked in Puerto Llano, and since 2013 she develops the risks analysis, environmental risk analysis, and operations for the production of new environments. Raquel, you have the floor.
Buenos días a todos y muchas gracias por habernos invitado a
Well, good morning, and thank you very much for inviting me to this presentation. I'm going to briefly comment on the environmental challenges that the fracking activities represent. I'm going to talk about how conventional exploring and drilling activity takes place, and then we'll talk about fracking itself, and then talk about the environmental challenges that it means.
Como veis, este es el sistema de los hidrocarburos.
Well, this is the system for hydrocarbons. For this kind of hydrocarbons to be exploited, we need a bedrock, and we need a migration process towards the more superficial layers, and that they will store in this sealing layer, so the hydrocarbon will not move any farther. So the rocks that produce hydrocarbon have this look. In the porous of these rocks is where we find hydrocarbons, weight of a bigger weights like oil or lighter oil, and they can have different sizes of porous. So the eye easily sees the ones that you see there in blue color. So here they are in millimeters in blue, and then if you're at the end of the room, you might not appreciate these other ones which are smaller. These are within the limits of what the eye appreciates. And then there are some others which are even smaller. We will need an electronic microscope to see them. There, at that very small scale is where we have these molecules that we are looking for, either hydrocarbons or gas molecules. And I wanted to show to you the different stages of this kind of exploration and drilling process. And we will prepare the site, first of all. Then we will design the well, then we will recover the well, finally we'll put it into production. And that is the time that takes longer. Once these deposit runs out of mineral, then we will move to another one. And we're going now to move to a non-conventional production. And as you appreciate on the right, the rock porous that we've mentioned are interlinked. What does it mean? If I drilled a well or a pit in this corner, I will be able to drain all the fluid that is in the pores of the whole of the room in all the walls, just by a difference of pressure. And what happens in a non-conventional activity, the pores, even though they've got hydrocarbons, they're not interlinked. And if I drill a well here and put a pipe, we'll only be able to drain whatever is around that drilling area or drilled area, and the rest will remain in the walls.
La fracturación hidráulica ha permitido extraer de forma segura petróleo y gas natural de las formaciones subterráneas durante más de 60 años. Es una tecnología que ha avanzado de forma continua para mejorar el acceso a estas fuentes de energía y reducir al máximo el impacto en el medio ambiente. Vamos a ver cómo es hoy en día este proceso que tiene lugar en las formaciones de esquisto a miles de metros de profundidad. El pozo se abre utilizando una broca y una tubería de perforación. A través de ella se bombea un lodo que enfría y lubrica la broca. El lodo también ayuda a reforzar las paredes del pozo y transporta los fragmentos de roca hasta la superficie. La perforación continúa muy por debajo de los acuíferos. Entre las aguas subterráneas y las reservas de gas hay miles de metros de formaciones rocosas impermeables y superpuestas que impiden cualquier contacto entre ambas zonas. En este punto se retiran la tubería de perforación y la broca y se introduce un tubo de acero que actúa como barrera entre el interior del pozo y los acuíferos. Luego se bombea cemento, que recubre tanto la cara interior como la exterior de la tubería. De este modo se crea una barrera de protección permanente y sólida que evita la contaminación de las aguas subterráneas y también que cualquier otro material penetre en el flujo del pozo. Una vez que se ha instalado la primera capa de revestimiento, se realiza una prueba de presión para asegurar que no hay fugas. La perforación continúa durante otro tramo. A continuación se construye una segunda capa de revestimiento de acero y de cemento y luego una tercera. De este modo se crea una barrera permanente que garantiza la seguridad del pozo y la protección del agua. Después, a unos 150 metros, por encima de las capas de esquisto, la broca gira y comienza a perforar en sentido horizontal a través de la formación rocosa donde está atrapado el gas. Para ello se utiliza un taladro especial que cuenta con sofisticados instrumentos de medición y control. Cuando se ha alcanzado la distancia horizontal deseada, se realiza de nuevo el proceso de revestimiento y cementación. Luego se introduce otra herramienta perforadora que abre grietas en la capa de gas para permitir que los hidrocarburos entren en el pozo. Cuando se retira la herramienta de perforación, se bombea un fluido compuesto por agua y arena en más de un 99,5% y una pequeña cantidad de aditivos. El objetivo de esta operación es ampliar las pequeñas grietas que se han realizado en la formación rocosa. Después, el agua se retira, pero los restos de arena permanecen para mantener los orificios abiertos y permitir que el gas salga hacia el pozo. La zona ya estimulada se aísla del resto gracias a unos dispositivos de bloqueo y la fracturación se repite a lo largo del pozo. Una vez terminado, se retiran estos tapones y el gas fluye hacia la superficie. El proceso de perforación completo dura aproximadamente 2 o 3 meses, pero la fracturación hidráulica lleva solo unos días. Una vez realizada, el pozo puede producir energía durante un periodo de 20 a 40 años. La combinación de estas dos tecnologías, perforación y fracturación hidráulica, permiten extraer petróleo y gas natural de lugares donde hasta ahora no se podía, y al mismo tiempo reducir al máximo la huella de todo el proceso en la superficie.
Bueno, una vez visto el vídeo, ¿dónde se enmarcaría?
Well, so what will you, now that you've seen this video, whenever we're doing this kind of a project, the fracking will take place after use of being drilling and exploring the well. Moving on to the environmental aspect of this presentation, I'd like to mention that there is a wide range of environmental regulations. Different institutions have drafted reports and organized different fora to talk about fracking. Once to analyze all this information, we've got to see what are the main consequences to the environment of this hydraulic fracturing. As I've already mentioned, this is a hydraulic way to stimulate a well that we inject a high-pressure fluid and we provoke the cracking of the pores in the rock, as we've mentioned. And we use to do so fluid, which is mainly water coming from superficial sources or under earth water sources. It's got to be transported to the well. Once we've done the fracking, when on the surface, we collect a returning fluid, which will be mainly water as well, that we then have to take to the place where it's going to be treated, and then we will get rid of it. We dispose it either in a superficial area or underwater. So when talking about water, we'll take into account quality and where it comes from. Then it will have an impact on the air, on the noise it produces, dust it produces, and on the light. And then also will have a visual impact and also might affect to the geology of the area if there is a potential eventosis. And I'm going to basically talk about water and the possible earthquakes. Talking about water, we've got to see how we capture water, how we dispose the effluents and the kind of chemical products that we are using. We will have to optimize the operations in which we capture water, make it watertight, treat properly the effluents, and optimize the use of chemical products. Here, I wanted to mention two things which concern us. One is water demand. In the chart, you see how this fracking action took place in the Ebro hydrographic basin. And here you see the cultures that take place usually in this area. If we translate any data from fracking activity and we translate them into hectares per year, we end up with a figure you see in the at the bottom of the slide, which is the equivalent consumption as we have in this hydraulic basin. Then something which is also controversial is I'm going to try to talk even faster. She says, more than 90% of this is water, and only a small percentage is identified within this list of chemical products that are largely used in the industry, like in feed industry, bactericide industry, and in our daily life. But the exact list of these chemical products is very difficult to make public because it might be the secret of the success of your operation, as it happens in other industries. And now talking about the potentiality of earthquakes in this area, we advise to always work in a non-high seismic risk area, even though we've got to undertake a geological assessment and monitorize the area and have also a program or scheme in case of a seismic event does happen. Here we see the evolution in the industry, and there you see the orange areas that correspond to mining activities and also reservoir building activities. And up to now, we've only been able to prove that when building this kind of activities, only 3 seismic activities took place, and they were magnitude 3. We want to minimize the use of the space, and we will try to build new infrastructures. We will have to minimize the amount of sites, and we will try to design infrastructures together with other exploring and drilling companies working in the area. Here you see the evolution of how the territory was occupied since the year 1990 to the year 1913. There you see that the surface has been reduced. The number of equipment, you see them in red. They are also smaller and smaller, and also the store areas are smaller. And then we have new measures like the screens that you have all around the site, where we try to mitigate the pollution derived from the noise or the particles in the air. Talking about air, we have to cut down emissions. Then we have to optimize the transport systems and also minimize the distances and the transport volumes by means of trains or pipes, for example. And we might combine different transport means and avoid areas which are populated, highly populated. So here we analyze the main environmental issues related to fracking. And here we indicate the measures to prevent and mitigate this potential impact. So I've already mentioned most of these impacts are similar to those of conventional exploration and production activities. The key is to identify it on an early stage, so that by implementing the right mitigation and prevention measures, this potential impact can be avoided. Thank you.
Muchas gracias, Raquel, por tu interesante presentación, y disculpa un poco las prisas que os estamos dando.
Well, excuse me to hurry you up, says the conductor. And now last speaker is Jesus San Juan. He works for the Polytechnic University of Madrid, and he is Institutional Relations Manager of Airbus Defense Space, CAS Space, a subsidiary of CAS Space, where he represents the company and also provides support to strategic communication and business development plans. He always was a business development manager in the fields of systems, and he also worked for 10 years in France, first as a satellite system engineer for Alcatel Space, and also he was head of the Department of Aerospace. You have the floor.
Muchas gracias, Maite, por tu presentación. Y bueno, quería dar primero las gracias a Mafre por esta coordinación.
Well, thank you very much. I deeply appreciate Mafre for inviting me, and also thank you to the organizers of this magnificent event. I'm going to talk about engineering in the field of the space industry.
Quería comenzar por hablar un poco del contexto, de cuáles son, hablaros un poco también de las empresas españolas dentro.
I will also like to mention the situation of the Spanish companies within the Airbus group. I'll talk about trends. I'll talk about how we manage risks in the space field or industry, and then talk about challenges and conclusions. Well, this industry in the world is 200 billion euros business, and most of it is communication satellites and broadcast business, and also Earth observation business or activity. The space is highly technological and transversal because many of the developments done and their application can be then applied to other sectors of industry. This is a sector which is well dimensioned, it is highly productive, and it creates high-quality jobs, even in spite of the financial downturn. And a large part of this sector depends on institutional budgets, but also a part is commercial, purely commercial, and it is growing. On the left, you see the structure of the upstream sector. There is where the flying objects are developed, then land field, where we do monitoring and follow-up, and then another part which is increasingly important, which is related to the operators, telecom operators, and also Earth observation activities, more and more important. And now we've got also services and applications, which is increasingly important. Within the world context, the North American market has decreased. It used to represent half of the world turnover, and in the past it used to be more than 75%. Now there are new actors, new service providers in this field, and we're moving from very big satellites and complex missions to smaller satellites and simpler missions. The business opportunities have been there for a long time, and they're hoping to see the light, like space commercial flights and other applications like those related to the Earth observation and communication. There is a reduction in the launching prices, and we demand more flexibility, both technical and operational, but we request at the same time the same security and safety. And also due to this reduction of the price, we're trying to use more reusable technologies. More and more we see companies appearing in the market which really provide small satellites and cheap launchers. And then the classical products are facing new trends. What used to be a satellite in the past, now with the new products which are cheaper and but that last for a shorter period of time are the new alternative. And then in the downstream part of the field, we now have navigation, Earth observation, which are now going to be part of the business in the next years. In Europe, this represents a small part of the industry. It is a well organized sector with the support of the institutions, the national space agencies in the main countries like France and Germany, basically, and also lately United Kingdom. And with the European Space Agency being the driver of this field, and for now some 6 to 7 years, we're sharing this leadership in technological leadership in between the European the Space Agency and Europe, and a large part is devoted to the development of to technological developments in the field, basically, of navigation, like Galileo or Copernicus, to observe the Earth with the launch of the Sentinel satellites, and also with an active surveillance of the space, leading, of course, to the issue of space junk. And now we see that we account for 10% of, in Europe, of the global market, and some emerging countries, such as Brazil and some other which are no longer emerging, like China, they're developing their own space policies. And somehow this is going to create fierce competition and to cut down the cost. Spain, this is a small sector, but it is well dimensioned. 70% of its turnover is devoted to exports, and there's a high degree of investment in R&D and innovation. We've got new developments both in the flying activity or in the land activities. We can integrate overall systems both to fly or to survey from land. These space vehicles were for satellites and launchers, 700 million a year of turnover, and more than 3,500 people working in this field. Well, this is a very quick overview within the Airbus group. The three main companies. Airbus is producing airplanes, civilian airplanes. Then we've got Airbus helicopters, and recently created last year a company which is Airbus, the one combining the electronics, space system, and intelligence and security and safety systems. So these are the main heads: so CRISA, Casa Espacio, y Infoterra, SGA. As I've mentioned, within Airbus Defence and Space, we can provide whole satellite systems to the Ministry of Defense and Industry, and we can also develop some toolings and develop microwave antennae and reflectors and other devices for launchers and satellites. CRISA, this company, is focused on flying electronics to control and manage the power of these devices. And then we've got Infoterra. They work with radars and satellites. Some of them they've been done by Airbus, and then what they do is make use of those images and also get money from the copyright of the images that they provide. Well, the different business lines and trends. Well, nowadays, launchers, it's quite a peculiar industry. The issue here is that to fight the Earth's gravity, since engines don't run without fuel, in order to take 6,000 kilos of fuel and put them into an orbit, we need a huge launcher, and that produces a very high cost. The launching might cost 90 to 100 million euros. So during your presentation, Luis, I was remembering that the stretch limit to 50% was the criteria used to define and design the states for the bridges, and we have to find the Earth gravity. So we have a different fight. And the life cycle of launcher is smaller than that of a bridge, so that we don't have the fatigue issues that you do have. We have to use fuel with a compromise in between its volumetric mass and the push it provides. So we use hydrogen and oxygen with a small volumetric mass, but that makes us create deposits which are huge. Apart from hydrogen and oxygen, I've got to say also that hydrogen and oxygen are highly flammable, and we are also within satellites. We also use nitrogen peroxide and other components which are highly toxic. So this is a very special industry. When talking about communication satellites, well, not to get into all the details, because I've got to be very fast, I've got to say that, well, the KU band is really congested, so now we're developing the new KA band, and the objective is to foster the reduction of the digital fracture, because we're going to be forced to use satellites for communications because the Earth communications are sort of saturated. We need more flexibility. We need satellites to be able to be reset when in orbit. So we need active antennae and aerials, and this makes the satellites be more complex. To reduce the cost of a satellite, we've got to make them more recurrent. So we are using low orbit constellations and trying to reduce the manufacturing cost. The present situation is that a large part of this technology, which is vital for the control of borders, to know the weather and the climate, and to prevent catastrophes, this requires platform and constellations which are more agile and antennae which will be broadband or even of broader band. We also need miniatures. So, I mean, we've got to face many challenges. And quite quickly, I'm going to talk about the impact of the new space regulation coming from Europe. It's going to have the Cleaner Space Directive, a high impact because we might be running the risk of breaking the supply chain. We always sort of produce very restrictive regulations in Europe. They make us be better and more respectful towards the environment, but also they produce a great challenge. I'm going to skip some of these slides. Cleaner Space also deals trying always to make this industry be more sustainable. They always try to find a passive way to take back home all the waste or space waste that we produce. Well, this is quite risky. I'm about to fall. Excuse me, but I always fall down and break my head. Well, okay. The risk, even though if it is defined by the American Space Agency or any other institution, a risk is the probability of things not happening as we expected them to happen, or as we had designed them. We might go wrong with the design, and we might also be wrong when dimensioning the loads that were not duly specified. Also, the qualification, maybe it was not determinant, even though many people thought it was right. Also, risk related to production, integrations, and so on. We've always had this bottom-up approach. We search every component, individual failures, we identify critical points, and then we went into one failure mode only. And during production, we would make this element go through a huge amount of tests that make these products be very expensive. This is not robust when facing human errors or software errors. It is not adapted to some dynamic situations. As you've mentioned, this is an issue when you are managing risk, and it is quite expensive to manage. Nowadays, more and more, we are adopting a quantitative approach. We have also this kind of risk assessment in low-cost activities like nanosat and small satellites that are going to be used as technological sort of front runners. They only weigh up to 150 kilos, and the high-resolution equipment they take on board, or even navigation aerials or antennae can be put on board of these satellites, so they are very useful. Another example that I've given you, even though you can, of course, have a look at my presentation on your website, here you see how we do a risk assessment according to a typical chart where we identify the risk, we see the probability and the consequences according to whether there is a component loss, of a subsystem loss, and so on. And then we adopt the preventive measures to avoid this. In the space world, the issue is that this technology is quite complex. And whenever some of these antennae fail, we cannot send some people to go and fix it because it is maybe some 30 kilometers away in height. Then I'm just going to sort of give you a short overview about the launching operations. We're talking about the security on board, both while launching them and then while flying these devices. A launcher is 800 tons of weight and is high as a 12-story building, and you've got to make this work in a very safe way. So we've got to see how we manage risk, how we verify the nominal drop of propulsive stages. We've got to also respect regulations. When some other space agencies manage our products, maybe the load will be bigger, but we're too strict when evaluating risk, and we request to be the launcher very visible. And maybe some other agencies are not that strict. That's why our performance sometimes is not so good. Of course, we've got devices of neutralization on board, also some algorithm within the software that you feed into the satellite in order to be able to destroy it if necessary and reduce to zero the eventual damage caused to people. And then this is about the different actions that we take to guarantee safety and security both during flight and on land. And conclusions. The launchers industry and satellites industry is getting ready to face a new stage with launching and service prices which will be smaller. Now the present tariff is like 15,000 euros, and with the new companies that are sort of cutting to half these prices, in Europe we're going to be forced to react and to improve a lot our processes to make launches that will be more flexible and cheaper, and also, but still being very safe. And then talking about satellites, telecom satellites, the core business, both for launching and production of these satellites, the core will be 4 to 5 ton satellites. But now there is the electrical propulsion that is coming on stage, and that means 2 tons less of fuel. It should last 15 years, and it's going to be a bit more complex, the injection in the geostationary orbit, because usually during a launching, 2 weeks later, the telecom operator starts putting into place its business plans because the satellite is up there and running, the aerials are working, and it starts really to sell its telecom services or broadcasting services. Now with the electrical propulsions, to gain the geostationary orbit, this will take up to 4 or 5 months. So the telecom operators should be more patient in the future before they start exploiting their satellites. Well, the Earth band is saturated, and this might also promote the use of this electrical propulsion. And then about business. There's a new trend towards telecom constellations and Earth observation. This is about providing broadband with the small satellites, but with a number of constellations, quite a high number of satellites in every orbital plane. So every group of satellites would cover a certain region and provide that coverage. And this is the difference. We used to have a big satellite that will last for 15 years, and these constellations will only last for 3 to 5 years. So we will have to renew them quite often, and also we will have to replenish often these constellations. And then there's a new business, that of the massive production of this kind of new elements at low cost. Also, the industry is facing ambitious missions in the short term, like commercial flights, and maybe also this. Maybe one day we will see hotels where we will be able to enjoy a very nice sunrise. I don't know whether this will be true or not. In this kind of project, half the price is the production and half of the price goes to the launching. And this will be evolving in the future. And whether we can guarantee these missions, usually launchers, they have to extend their civil responsibility insurance, and then the telecom operators for satellites usually hire their building insurance, and for a time also the orbit insurance. As far as I know, and more in the operational side, I think we're talking about an 8 to 9% of the cost. This is the percentage for the insurance. Usually in the Ariane division of my company, there we build a launcher which is really unbeatable, and I think that is why it is so expensive. In fact, I think that the SpaceX, and also because it's not so much edited, the insurance is a bit higher. We've got to develop a new model to guarantee emissions, these new emissions. It's not the same to provide a service with a 6-ton satellite that should be there for 15 years than when you do it with a constellation of hundreds of satellites that will only last for maybe 4 or 5 years. Which might mean a new way to provide a guarantee and an insurance for this kind of a small element. And also that 8 to 9% should increase, of course. The downstream sector will also play a bigger role in this industry to optimize the Earth observation and navigation activities. And to conclude, the presence of orbital debris or waste that some 8 years ago was some 20,000 particles, but there's been a clash of the Iridium satellite, and there was also a test done by the Chinese. They've launched a weapon against the satellite that it was no longer in use, and now we talk of a higher amount of satellites, particles of debris, which are beginning to mean a risk to these satellites in orbit.
Muchas gracias, Jesús, por tu presentación.
Thank you very much for your presentation. And even though we're quite out of schedule, if you have questions, please be my guest.
Decía que cuando estamos perforando y llegamos a
I
una
was
capa
saying that
acuática,
when we drill, we reach an aquatic layer. And what happens with the sludge that we use for cooling?
corremos el riesgo de contaminar ese acuífero
With
o hay algún
those
tipo de veneno
that
que
sludge,
contaminar?
can we pollute the aquifers?
¿Escuchas? Cualquier pozo que se está perforando
Any
a día de
well
hoy, a
that
nivel
is
mundial,
being
en
drilled
función de su profundidad, es
today,
bastante probable que esté
depending
en
on
las
the
circunstancias que
depth,
tú comentas. Esto no es
will
algo típico
suffer
de la
from the
fracking incluso.
circumstances you
Digamos que
mentioned.
la
This
capa
isn't
freática,
specific or inherent to
habitualmente la
fracking.
podemos encontrar en
The
profundidades
phreatic
menores o
layer
superiores a 1
can
kilómetro,
be at
y
a
que
lower or
cualquier
greater depth
yacimiento,
than
y
1
más los que se
kilometer.
están perforando hoy en día,
Any
que los más sonoros ya están
deposit
descubiertos,
or
los
site,
tenemos que buscar en capas más profundas,
and the
en
deposits or
zonas
sites that we're
más,
drilling nowadays are
remotas,
deeper
todos ellos
down.
normalmente en un porcentaje muy
And
elevado
what happens
atraviesan
is that
zonas
in
freáticas.
most
Para
of
ello,
these
existen
deposits, we
diferentes
drill through
técnicas
phreatic
de
layers.
estanqueidad del
And there
pozo.
are
Uno
different
de los
techniques
aspectos
to
que
ensure
yo
the
he mencionado en la
tightness of the
presentación
well.
en breve esquemita
One
que
of the
se veía en la parte
aspects
de cómo
that
proteger a los
I
recursos hídricos,
described
en
in
donde
my
a la hora de
presentation
hacer esas cementaciones
dealt
se
with
van
how
superponiendo
we
diferentes
concreted
capas
in
de
such a way
cemento
that we
para tener
built
un
on
especial
different
cuidado
layers of
en la zona
concrete.
freática que tú
And we're
estás
particularly
atravesando cuando
careful
estás haciendo la
in the
perforación. Sin
phreatic
embargo,
layer when
cuando
drilling.
perforas a más
When you
profundidad
drill at
y
greater
pasas
depths,
esas zonas
and
más sensibles,
when
las
you
composiciones
pass,
de estos
and you
cementos que
leave
estamos
that
utilizando para
more
mantener lo que es
sensitive
la tubería,
areas,
si no la tubería se
what
vendría abajo por la
happens
presión que ejercen las otras capas
then
del subsuelo,
is that
cambia de composición.
there's a change in
¿Vale? Tiene una
composition.
composición específica
It would
y
have a very
redundante
specific
para evitar
composition
esas
which is
contaminaciones.
redundant in order
Asegura que
to
no se contamina
prevent pollution. So you
lodo,
can
no se
ensure
mezclaría
that
ningún
the
gas.
sludge doesn't come
En
into
principio,
contact
si
with the
todo está
water.
bien hecho, no.
That's right. If things are done properly, there's a tightness and there's no
No
contact.
tendría por qué.
And thus, no pollution. That shouldn't happen.
No sé si hay alguna pregunta más.
Do we have
A mí
further
me gustaría
questions?
preguntarle a
I'd like
Luis,
to
que nos ha
ask
enseñado, nos ha
Luis
mostrado
something.
una fotografía de
He
un
showed us a
incidente.
picture of an
Quería
incident,
preguntarle un poco más si nos podía
and
simplemente
perhaps
indicar el motivo
you can explain to us
dicho
the
problema.
reason why it occurred.
Bueno, la pasarela
That was the passageway
todavía no está del
that
todo
had
claro,
collapsed. It's
bajo
still not
investigación,
clear.
aunque
It's
ya
under
pasamos un par de
investigation.
meses, aunque ya se apunta
It
a
happened a
diferentes causas.
couple of months
Y
ago.
fundamentalmente hay dos.
Different
La
causes
primera
are being
es
considered.
probablemente un
It is
defecto,
probably
yo no
due
lo
to a
calificaría de defecto de
defect,
diseño,
a
probablemente
design
sea correcto,
defect, or
aunque
perhaps
sí
not a
algo
design defect,
limitado.
because the
Vamos a
design
decir que muy justo, muy
isn't
cerca
incorrect, but
de-
is quite
del
limited.
Y el segundo gran
And the
problema,
second
y
main problem which led
vuelve
to
un poco
this
sobre la ponencia
incident,
y sobre alguno de los aspectos
and that
comentado,
refers to one of the main topics of my
formación.
presentation,
El
has to
problema
do
ha
with
venido, por
training.
un desapego inadecuado de las
This
estructuras.
incident
Este tipo de estructuras
was
son más
caused
esbeltas
by the lack of
y un
training
proceso de
of the
desapego,
operators.
no adecuadamente
The
realizado, en
fact
este
that
caso,
the
muy
structure
probablemente por falta de
wasn't
formación del
adequately
personal operario que llevó a cabo este
handled due
desapego,
to the
ha provocado
lack
un
of
efecto
training of
dinámico
staff,
sobre la pasarela.
led to a dynamic effect on the passageway, dynamic effects on passageways
Son muy importantes,
are very, very substantial and important
un incremento
because
de
they
la
lead
carga,
to an increase
sustancial.
in the substantial
La estructura
load.
está preparada para soportar una carga X,
So, if the
los
structure is
efectos dinámicos
prepared
pueden
to
provocar que la carga, esa
resist
carga X se
an
multiplique
X
por
load,
de 1,7
As a result of the dynamic effects, that number can be multiplied by 6 or by 8. And if these values hadn't been envisaged during the design stage, well, problems such as the ones that occurred can arise. There was an impact on the metallic element. This led to a plastification of steel and ultimately to the break and to the collapse of the bridge. Thanks very much, Luis. I'd like to thank the speakers for sticking to the time. And some of them have had to rush. And I'd like to thank all the members of the audience for their attention. Thanks very much indeed.